Good morning, good afternoon, good evening, where everybody is, wherever you're at on this planet. My name is Jim. I'm coming to you from actually Denver, Colorado. It's a beautiful day here. And I'm excited about this talk. I've given this talk, oh gosh, a couple times already. And I think I actually understand it now. I know I'm joking. We're going to get into the architecture of CockroachDB. And we're doing so it'll show some of the value of what Cockroach can actually deliver for people. But I'd really like to make this as valuable as possible so that, as you're going forth and building your own distributed systems and applications, maybe some of the principles and the learnings that we had here at Cockroach might be applicable to the way that you think about your code and what you're doing. For me, it's all about building a distributed mindset. And what that is, I think when I was first introduced to distributed systems, it took me a while to actually really figure out like what was troubling me. And it was this physical nature of data and compute and what that means. And so along the way, I hope this is valuable in a general sense beyond just kind of, how CockroachDB can help you. And hopefully valuable from a point of view of learning some of these core concepts. So I'm actually going to go on screen here. So before we get started, this is kind of intermediate to advanced. We're going to get into MVCC. We're going to talk about Raft, some of these core concepts. We're going to talk about pipelining of transactions. These things aren't too simple, but we're going to talk about these things today. My name is Jim. I'm actually principal product evangelist here at Cockroach Labs. I'm joined in the background by my friend Keith. Keith is going to be in our chat and our QA the whole time. So if there's anything that you want a little bit of a deeper explanation about, please do use chat and QA. I hope there's a lot of questions because there's some really cool stuff here. I think my explanation will be good for the amount of time we have. But if you need more, oh gosh, please by all means. Keith is brilliant, knows these concepts extremely well, and can talk about them with you in those channels. I'll also be monitoring chat and QA along the way. So if there's something simple that I can throw into the conversation to help explain things, I'll try to do that as well. But yeah, please do engage. It'd be great. And then finally, at the end of the session, I know there'll be a survey. Please do take that survey. We take these things very seriously here, always trying to improve. Like I said, I think this session has improved infinitely by some of the feedback that we've gotten over the course of time that I've given this talk. So thank you, everybody, for joining. And with that, let's get on our way. Why are we here talking about this? Well, for us, this concept of a distributed SQL database and being cloud native really comes back to kind of agility and efficiency and being able to use kind of cloud resources. And as the world has kind of shifted our infrastructure into cloud and distributed systems, legacy databases and some of the previous kind of generations, they just don't fit this new world. And for us here at Cockroach Labs, it's a rebuild, it's a re-architecture. It's basically taking these things from scratch and saying, let's do this the right way for the world that we're going to live in. And so there has been this kind of, this entry of a new type of database, distributed SQL. Matt Aslett, my friend at 451 Group, came out and talked about this. For us, these are kind of core distributed systems principles, right? These things need to your systems, and I don't care if it's a database or not, they need to scale. They need to remove operational complexity. They need to be always on and resilient. But for a database to be, a distributed system, well, for us, if we're going to be a relational database, we have to implement, I believe standard SQL is a non-starter. You have to have that. And then another core concept in distributed systems is this physical nature of data. I think when we used to think about databases and our systems in general, we would think about the logical model. Like, what's the logic? What do we want to actually accomplish? Well, in distributed systems, you have to think about the physical model as well, especially with data, because, well, the speed of light is no joke. You can't beat that. And so for us in a database, that all meant about how do we tie data to a location so that, data for German users lives in German servers so that they have this kind of low latency transactions and right now. And we're gonna talk about that and how we do that in a database, but I think some of these concepts do apply more broadly. We do share some very common distributed principles with Kubernetes, if you're familiar with that as well. And I think, if you think about the way that Kubernetes was built really as kind of, core infrastructure Within Google, we are a descendant of Google Spanner, which is the database they built to kind of run on Borg in the back end. So, I think this importance of the distributed architecture is becoming more and more apparent as kind of organizations move to this world. So, real quickly, Cockroach, we are a distributed relational database. This is familiar standard SQL. We are wire compatible with Postgres. But for scale for us, we're a node-based database. So you simply spin up a new node of Cockroach, you point it at the cluster, and the database consumes that node. All the while, each one of these nodes is an endpoint. I can access the data through any one of these things, but it looks like one single logical database. When we write data to Cockroach, we're writing data in triplicate. And we're going to talk about exactly how that works. But by simply just adding new nodes, we aren't just increasing volume for reads, we're actually increasing volume for writes as well, which is actually a really, really important point because every node is an endpoint. Now, that gets really difficult when you start to do these transactions at scale, right? So, and we implement serializable isolation so that we're going to guarantee data is correct. Again, we're going to come back to exactly how we do that in this. Now we can scale further out. We can scale across multiple different regions, across Kubernetes clusters if you wanted to. And this is all going to look like one single logical database. Again, so you have endpoints in different regions of the world, but the entirety of them working together to appear as a single logical database, right? Any endpoint can find that data. We can even do this across different cloud providers. Keith and I did a whole demo on this a couple months ago. I thought it was really cool. Like, this is a true multi-cloud application, one single logical database deployed across multiple different cloud providers. Sure, there's definitely some complications around networking and some of these things, and there's some things around how you get around that. We definitely have best practices, but you can do this, right? Which is kind of unique for us, and this allows us to survive really any failure. And again, we're going to talk about this. How do you survive the failure of a node or a rack or AZ or even an entire region? Well, when you write data in triplicate, it really comes down to how your data is arranged across this physical nature of what these things are. And we'll show you how we do that in the demo. But again, every node is an endpoint. So if I asked a node that's, say, in a cluster in US West, it's going to be able to access this data that's over in US East, right? You see these three copies of these data, Kimball, Madison, Stewart. But if you access that from, say, cluster East, well, you're going to have a lower latency access, right? Because that node, that user accessed their data, user Kimball, Spencer Kimball, our CEO, asked his own data, and he's living in the East Coast, right? And so those are some of the things we could do. Again, single logical database, multiple different regions, multiple different clouds, but we're doing things to optimize access and the way these things work, right? There's just a fundamentally better experience for your users, pretty easy to configure and kind of deal with. But we also know if you're going to implement a database, well, there's integration, there's management, there's cost-based optimizers, query inspection, security, all the different tools you would expect to have in a database. We spent a lot of time building that out as well. There's some cool stuff in the architecture, but all this kind of, mundane, important stuff also has to be there. And we've gone to great lengths to do that. And we'll point out one last thing on this slide, and that's our documentation. Everything that I'm about to go through today is written in almost poetic form in our documentation. If you're really interested in how transactions were, the life of a transaction in our documentation is a great place to go check out. But in general, I think the world of our documentation, and the team does a great job. And so, that's always a great place to start. All right, so let's get into the architecture and how this all works. So ultimately, Cockroach and CockroachDB is implemented as a database on top of a database, and it's exposed as a database. So it's kind of like the database of a database trying to be a database. I don't know if you guys ever, anyway. So ultimately at the core of any database is really kind of three layers. There's storage, there's SQL execution, and then there's a language. Well, I've already talked about the language. The language we've implemented and what we've become is really wire compatible with Postgres. So you can access this as straight up, relational SQL that you've been familiar with for a long time. There's some caveats there we can talk through as well. But you can go check out our SQL compliance and our SQL coverage in our docs, and you go check that out. Where this gets interested is really at the storage and the execution layers. And that's what I'm going to talk about. At the lowest layer of a database is storage. And ultimately, every table in Cockroach database is implemented as a KV store at the storage layer. This is not exposed to our end users, but it's an implementation architectural choice that allows us to do some really cool things. So every table, let's say this is the dogs table, it's basically ordered lexicographically by key. So the key is each of the names of one of these dogs. Now, in the old world, what we had is kind of this indexes and a table, right? And in memory, basically, you would have inventory table. You would just keep appending data to the bottom of this, right? And like, okay, and in the physical space, and then you would have this index that had pointers to memory locations, and that's kind of how you saw this. Well, this works really well in a single, right, server or a single physical location, but how does this work when you start distributing data all over the place, right? And so this is the challenge that I think is dealt with this kind of KV store. Now, the KV store, there's a lot of things that we benefit here, but it is really basically the way in which we store data. It's really easiest to just show this. So if I think about a table, let's think about this dogs table, right? And so here's my DDL. It's like, okay, I'm going to create DML. I'm just going to create this table. It's an ID, name, and weight. And over on the right-hand side, you see some entries, right? And that just looks like a normal table that you and I may think about from a relational form. When we store this, however, what we're doing is we're taking each of the rows and we're saying, look at, in the KV, the K is basically going to be a compilation of a couple different things, right? We're going to take the table name, we're going to take the ID, and we're going to take a column. And what we're going to store there is basically the name, Carl, right? Dog 34 weight 10.1. So every row is now broken down into KV. Now, again, we don't expose this. What gets exposed is the table, right? But this allows us to do some really cool things. And we can actually overload this key with lots of different things. And we'll show you how we use that to some advantage a little bit later. But this is really the storage and how this stuff all works in the end, right? So, okay, the second record, dogs 7A, Downey, right? And so you just go through this whole thing. So basically the entire things. Now, if you look at the values here, right, what you're seeing is this ordered set of KV, right? If I just basically did an order on these things, this is exactly how it's going to come out. So if I put in the next record, we know exactly where to put that. And so another really, really important concept here, that everything is ordered when we actually go down to the storage layer. That's what's going to allow us to actually find this data very quickly across a distributed environment, right? We do actually do some much deeper encoding to create some massive efficiencies. I'm not going to get really too deep into that, but you know, this ordering is the key concept, right? So we have this ordering, right? And now, if we think about this entire table and the way it's ordered, right? I'm going to basically now divide the table up into these something we call a range. You can think about it as a shard or a tablet or a slice. I think lots of different companies call it different things, but we call it a range. And we break down the table at the KV layer into these 512 megabit ranges. And so you'll see the first range is, say, the first 4 records, the second 4, right? We have this kind of, I guess, orange, blue, and red, right? And so what we've done is we've chosen this size very scientifically, because this allows us to kind of amortize some of the overhead that we have in managing these ranges and how easy it is for us to move these things around in a cluster when we need to do that. And we're going to show you how we do that, right? And so, but it's really important to understand so that if I grow a table, I just keep adding ranges to it, right? And we keep inserting things. So let's go through that, right? Oh, by the way, if you have ranges, well, we also need an index structure to locate these things. So we've implemented something that allows us, it's very much like a B tree, if you're familiar with that. And that's how we kind of find things. Now, so what happens when we want to insert a new record into this table? Well, I go through my to find this. Okay, great. This is Sunny. We know where it's going to sit in this ordered key space. That's the key. And we're going to look at the red range. The red range has space. So great. I'm going to insert that into the range. Great. Insert. Great. Done. Beautiful. Okay. Now what happens when I want to insert another record? We want to insert Rudy. That's the key. There's no room. What we're doing is we're going to just split that range. We're going to take it in half. We're going to split it in half. We're going to insert Rudy. We're going to say, this is great. We're good. We're good to go. We don't actually do this in real time. We do it as a kind of a little bit of a cleanup process. We'll let you go a little bit beyond 512 so that we don't hold up transactions. But what we've done is we've basically just automatically sharded this database, right? We've just basically expanded the amount of range and the amount of shards. Now, these ranges are going to be distributed across physical locations, right? And that's the key. That's the trick. But the database is taking care of this, and it actually changed, you know, all the different things. Now, how do we then distribute this data in Cockroach, right? So let's get into the second concept So that's what we're doing at the bottom and how we store. So let's get into the second concept, and that's Raft and the Raft protocol. Raft is a distributed consensus protocol or distributed consensus algorithm that allows us to kind of deliver these kind of atomic writes and how we actually distribute these ranges and ensure that we're going to get consistent reads across the board. Raft is an important concept in distributed systems. And if you're a student of distributed systems, I would recommend checking it out and reading a lot about it, because it's actually extremely interesting. If you're already doing distributed systems, you're probably familiar with Raft. You're probably familiar with something like Paxos or Calvin or one of these other things, right? And so I think it's kind of interesting to check out these things. We're going to talk a little bit about MVCC, Multiversion Concurrency Control as well. That's another interesting one from distributed system point of view. But Raft is implemented as kind of this system of how do we actually get quorum and how do we get consensus across different participating members of a group. And to do so, well, you have to implement, really kind of a odd number of replicas. And we're going to do that because, well, we're actually going to do something called a quorum, right? So like, basically I'm going to have to say like, hey, look at 2 of 3 of these nodes, 2 of 3 of these copies of the data have to agree, because the third one's going to have to just go along all the time, right? So first of all, it's going to start with an odd number of replicas. Raft is very chatty. These replicas are talking to each other all the time. They coalesce heartbeats, so they keep in sync. But most importantly, there's this thing called a Raft leader. And the Raft group elects a Raft leader. So one of the 3 of us has to be the leader. Great, you're the one. If the leader dies, then the remaining 2, Raft replicas are like, hey, we need another copy, create another copy, and now let's nominate a Raft leader here. I'm not going to get too into how that works, but really the Raft leader is special in that it coordinates basically how commands work and what happens within this Raft group. And really the Raft leader is the only one who can really serve at this authoritative up-to-date, right? Like there's followers and then the leader. And so it's kind of a really, really important concept, but allows us to do this kind of atomic replication of when we do writes and when these things happen. Because when we write data into this table, we're going to ask the Raft leader to say, hey, write this data. And it's going to coordinate with the followers and say, hey, y'all got to write this data, make sure it's done. And it's going to get this consensus. 2 of 3 are going to write. But we're also using Raft to actually help us distribute this data within the database as well, within these physical nodes. Oh, by the way, if you want to actually go check out Raft and how it works, man, this is a great website. If you go check out the secretlivesofdata.com, they do a really, really good job of explaining kind of how this works, how Raft leaders are elected, so it definitely worthwhile to go check out. But we're using Raft to help with kind of distribution of this data, right? So I went through storage, went through one of these core concepts of Raft. Now, how are we using this stuff to actually distribute data across these physical locations? Well, where we place these replicas, right? When we write data into a cluster, we write it in triplicate. We're using Raft, right? There's 3 copies of each of those ranges, right? Remember the first range, I had 3 copies. Second range, that red range, I have 3 copies of that somewhere in these physical nodes. I could have hundreds of them, right? The database is just management. Where we place these things, the 3 copies really depends on a configuration of what you want to do. And by the way, we could have 5 replicas, we could have 7, 9, depending on what you want to do. There's lots of different reasons why you'd want to do that. But let's just talk about the 3. Maybe there's lots of reasons why we'd place things in different places within a cluster. Let's just talk about diversity. And so when we're placing things in a cluster, let's say the first range, we're going to go write this across. Here's a 4-node cluster of Cockroach. We're going to write this data across 3 nodes. We're going to write the second range across 3 nodes. We're going to write the third range across 3 nodes. Oops, there we go. So basically what we've done is we've balanced the data from a volume point of view across the various different nodes. Now we're going to actually write this across different nodes so that we can survive the failure of a node as well, right? I still have 2 of 3 of the copies. If one of these nodes went away, I still have 2 of 3 of the copies, and I can still basically get quorum, right? Because I have 2 of 3, right? And so we're doing this basically for diversity, and we're balancing how this stuff works. But Cockroach is actually smart enough to actually understand workload as well. So maybe there's a range that's a hot range. This muddy record is being accessed all the time, and we know the volume through that. The number of queries that are going through that range are are way high. And so we're taking, usage metrics and we're taking heuristics, and we can actually isolate that on nodes where there's not as much traffic. This is a very generic example, but we can now start to isolate things based on load as well, right? So we get optimal performance across the entirety of all queries across this table and all the other tables that are in the system. Typically in a CockroachDB implementation, you're talking about hundreds of thousands of ranges. And so there's some very, very complex kind of computation stuff going on in terms of these things as well. Mohan was asking, can we run a database on a Kubernetes cluster in the chat? Absolutely. In fact, this is a database that was actually built in a lot of the same core principles. You would spin up an instance of Cockroach in a pod. If that pod dies, well, it's going to come back, right? Kubernetes is going to bring it back. The database is going to heal itself. We'll get a little bit more into how that works. And then there's some slides at the end, but absolutely. This is on Kubernetes. So you're managing it the same way you manage compute and everything else in Kubernetes. It's not on the side of it, right? And so that's kind of a core concept. And sure, Keith can provide more volume or more color on that as well, but definitely, y'all. So another way in which we actually place data here is to help us tie data to a location or map data to a location. And there's lots of different reasons you want to do that. Maybe you want to tie data to location so that, like I said before, my German users have really quick access to my data because all the data lives there, right? The Raft leaders and the copies live there. Or maybe I want to copy in each region, but the Raft leader in one spot. Or I want to diversify so that I can actually survive the failure of an entire region. It really comes down to what you want to survive and how fast you want your data. Now, in Cockroach, what we're doing is we can take a column and we can actually insert that. And remember the KV in our store, the storage story earlier? Well, what if I took one of the columns and it was like where this dog is located, and I overloaded that into the key? Well, now the sort on the table is going to use that location value or whatever value you want. And now the sort of all the records into these ranges now identified by basically where we want to store this data. And so when we spin up a cluster, we simply say like, look at this cluster is named X. And sure, it's named like US East, or it's named, part of the US West range, right? We actually assign it to a location. And now when we sort the data, we can now make rules at the table level or at the row level for where these things need to live based on how fast you want the data and what you want to actually survive. And so we're using the K and the KV to actually now segment the data and move it into different places so we get jurisdictional control. Sometimes this is good for people who want to meet like data privacy regulations, that sort of stuff as well. But underneath the covers, this is the value of basically being a database on a database. And this architectural concept at the lowest layer that allows us to do some really cool things. So how does scale work, right? I talked about you just spin up a node pointed at the cluster and the database takes care of it. Well, yeah, the database basically said, look, I just added another node to this database. What it does is it starts to move data into there. So the orange range, it just balanced and moved copies in there. You've done nothing. You've simply spun up a node, pointed it at the cluster, and the database is going to take care of balancing. There's no manual sharding. There's no kind of resharding. The database is just taking care of this and managing this all underneath the covers, right? But the same thing happens when you lose a node as well. Things die. Regions fail, AZs fail, nodes fail, rack fail. So what happens when these things happen? Well, the database just basically, it resolves this issue. It comes back from it, right? So let's say node 3 goes down. What happens is in the database, the Raft leader recognizes that it only has 2 copies left. So this blue range, let's just say, that's located on node 2. Well, the Raft leader is there, and it says, hey, wait a second, I just lost one of my followers, so I better create another copy somewhere else in the cluster. And it does. And now I have, I don't have these under-replicated ranges. I now have full copies of my data. I have 3 copies still. And so I've just completely survived the failure of this thing going out. And I don't have any impact in terms of, how quickly I access my data and how this is all happening, right? And so in real time, we also can survive like these kind of small outages. Let's say something goes offline for, a minute or something like that. We can just actually use replay logs and make sure everything's kind of up to date and whatnot. So it's really, really cool. And that's how we can actually survive a temporary failure as well. Okay, so let's see where I'm at on time. Okay, halfway through. We're doing great here, y'all. So now let's talk about, I've now written data, I've scaled out the database, I have now survived failures, right? So what about transactions? And very early on at Cockroach Labs, our founders, Spencer, Peter, and Ben, all of them, like mid 300s at Google, been dealing with distributed systems for a long time. They really erred on building not just a globally distributed database that this could be. They make it work really well in a single region, or single AZ, or on my laptop, right? But they wanted to implement serializable isolation, so guaranteeing that data is correct. If you aren't familiar with serializable or isolation levels in the database, probably a pretty important thing to actually understand. So we've erred for that, and then how do we make these things fast and guarantee these things is the other side of the database. I think our ultimate competitor is always the speed of light. But how do you do these things when I have a record coming in New York, and I have the same account being accessed in Sydney, and somebody wants to make changes? Who wins, right? Like which transaction is going to win? And so how do you mitigate that in a distributed system, especially at the speed of light? And so a lot of the stuff that I'm going to talk about in the second half here is how do we actually get close to the speed of light from a performance point of view? But at a baseline, how do we actually just even mitigate a transaction? How does a transaction actually commit? Well, let's talk through that. So here we are, 4 nodes. Here's our ranges. And the Raft leaders are identified with a darker column around them. And I want to now insert 2 records into the dogs table. So I'm going to ask any one of these nodes. And so I call this a gateway, and it's in green here because I can ask any one of these nodes. Remember, any node can find the Raft leader and ask it what to do, right? So let's just say I ask node 3, that's the gateway, and I'm going to do this. Now, every SQL statement you write actually gets broken down into these statements, right? The transactional statements underneath in a database, right? So I'm going to begin the transaction, and the first thing I want to do is write Sunny. So I'm going to go find the Raft leader for Sunday. I'm going to say, hey, let's do this, and it's going to say basically, there's some special like rows in this range that allow us to track transactions and whatnot, right? And so we're going to say, hey, it's pending. Okay. Now the Raft leader is going to reach out to the followers. Come on, reach out to the followers. There we go. Oh, it went too far, too fast. Did it go? Where's my slide? Okay, it's reaching out. Gosh, it's reaching. It writes kind of a temporary record. It puts this temporary status on it. That's why it's kind of yellow. And it reaches out to the followers and say, "Hey, y'all, write this thing," and they too kind of write this temporary placement on it. That's why it's kind of in a different color. But as soon as one of the followers come back and acknowledge, I have quorum. I have 2 of 3. Great, awesome. I can now say that write is going to be good. I'm not going to commit the entire transaction until the second half happens, because now I have to actually write the second record, which is Ozzy. Okay, great. That Raft leader. Great. Okay, good. Now let's communicate out to your followers. Once you get an acknowledgement back, now come back to the original transaction and say, hey, look it. 2 of 3 of my followers have actually have come an acknowledgement on this. Great. I now do that. At this point, I have 2 of 3 all over the place. I can clear these temporary records and everything gets committed, and I can acknowledge back to the originating requester and say, great, this now happened. Now, look, lots of things can go wrong here. In fact, when building a database, it's not easy to build any of this, even in a singular instance, let alone a distributed kind of, writing in triplicate. And so we've been through a lot of the kind of corner edge cases around this. I'm not going to get into the failure modes here, but just kind of I just wanted to give you a sense of like, okay, great. Yeah, this is how we're using Raft to get this kind of, this commit, right, of this transaction, right? So it's completely atomic and nothing gets done until we have, full quorum across all the ranges involved in a transaction. This is a pretty simple transaction. Sometimes they get really, really super, super complex. Okay. Okay. So another kind of thing and a core concept, and I'm going to go through this a little quick, but another kind of core concept in distributed systems. And if you're not familiar with multi-version concurrency control, it's actually pretty important. Think of this as kind of the I in ACID transactions. How do we get this isolation of events? And so this is a little bit, I'll do my best to explain this. Actually, the Wikipedia entry on this is pretty solid, but I'm going to try to do this in a graphical form. And so there's a couple of things that are involved in committing a transaction, right? There's this transaction, right? That's what I want to do. There's a timestamp for this thing. And then there's a row of data or a record that I actually want to commit. Now, time is really important in this concept. And in Cockroach, what we have is, we're using a network time protocol, and we have some software drift around that so that we can actually, throughout all of the nodes in Cockroach, these physical instances, we need to maintain some sort of timing in here. Now, if you're really interested in how this works, I think our all-time most popular blog post was living without atomic clocks. And an atomic clock is basically going to use GPS, and it's like hardware to make sure all these things are aligned. But time is really, really important when you're doing these things, because that is ultimately what dictates the serializable in the serializable isolation, right? And so if we think about this, when I write a transaction, well, for a simple transaction, right, at time 0, we have this thing, we're going to write to the object. And so on each object, we have the transaction time, we have a read time and a write time, right? So in the first step, we're at time 0, at time 1, we're going to put the write over. It's going to create a temporary object, right? A copy of it so we can actually commit. And when I actually commit, so the temporary object is that write time at 0.1. And when I actually commit that thing, say it took 2 seconds, I now have a read timestamp. So this thing was updated and it's good. And I could send acknowledgement back to this transaction. But you'll see this read timestamp and the write timestamp are a little bit off. That's exactly right, because in the time it actually creates to actually do this thing, this temporary setup and make this happen, we need to make sure that we're in a good state. If anything comes in between, we're in a weird state, right? And so this multi-version concurrency control actually helps with that. So let's go into a case where there is a conflict, right? So I'm going to write and we'll reset everything. So at 1 second, we're going to write. So the write timestamp comes in at 1. I create a temp object so that we can actually do this kind of update without actually changing what's going to be read in the main object. At the same time, at time 3 now, there's another write comes in from transaction 2. Okay. You'll see the transaction timestamp is 2. It's going to come in at 3 seconds in time to the object. Now, what happens is the object says, hey, wait a second. That 2 is bigger than my read timestamp, which is 0. So that's off. And I have a write that's already going on. So we're using these kind of 2 timestamps on the object to mitigate what's going on in that object, because I have not committed my first write yet. And I have a conflict. So that's the conflict. That's what MVCC allows you to do. It basically allows you to identify when 2 transactions are trying to write to the same object at the same time. Now, we've done this in code. It is crazy, much more complex than my little colored objects that are on here. And if you really want to learn more about this stuff, I think the Wikipedia article does a really good job about it. But another one of these kind of core concepts, which I find really, really interesting. Long story short, transactions happen in order. It's a single checkout line at the grocery store, and only one person can go at a time. And that's really kind of what we're doing. And we're doing this in bulk and across, geo-replicated, transactions across the entire planet. So it's just a pretty good complexity in the code that is actually allowing this. I always do this. Also, I'm just a marketing guy, so I hope this made sense. I'm actually an evangelist now. So, okay. So we've been through storage, we've been through Raft, we talk about scale, resilience, and we did some baseline of transactions. Now a couple more advanced topics, right? When you, in the database, there's storage, right? And then there's this execution layer. And execution is interesting because in a traditional database, well, execution kind of always happens in a single stovepipe, right? And it's kind of easy to control. Back about 10 years ago, I got introduced to Hadoop and kind of how that works and the concepts around map reduce and how we can push execution out to lots of different nodes and then come back and reduce an answer and give it back to somebody. Well, we're doing a lot of the same concepts here in Cockroach, right? And there's a lot of things that we're doing special in here to make this happen. But, ultimately, execution needs to be distributed in a distributed database as well. You're simply not a distributed database if you aren't doing this. There's other databases on the market that call themselves distributed. Maybe they're distributing storage across multiple places and they're putting, these kind of wells on top of there. It's like oil that's everywhere. And yeah, I got distributed storage and I can read from everywhere. But what about writes, right? Distributed SQL execution is not simple. That's why people don't do it. And this is the real beauty, and some really amazing software engineering has gone into this. And I think it's really, really important stuff. But let's just talk about a group by, let's just talk about a count that we're doing of customer table. So here we have our data. It's distributed across these 3 physical different locations. I want to do the select. I'm going to basically send the select. I'm in Denver. I guess I'm being routed to the US East. It's going to load balance across my nodes there. I'm going to go and actually do this count. What's happening is this is going to now distribute these capabilities, the scan, out to the various different regions, right? From the customer table. And so now across all these scans, I can now do these very efficient scans, because remember in KV, I now have maybe I only want to do half of the countries, right? I actually, I can now do these really, really efficient table scans as well, right? And so we're going to push it out to each of the regions. They're going to do the group by, they're going to do the count. We're going to return the values back to the originating node, and it's going to return this back to the end user, right? And so what we've done is we've actually now taken this execution, and we're pushing it out to all the end nodes, 3, 4, 10, whatever you have happening in your region, right? Now, this is really tricky because you got to think about your queries a little bit different. If you're going to insert 10,000 records into Cockroach, do you want to do all your inserts through one node, or do you want to do that across 10 nodes, right? And take advantage of this distributed execution, right? And this parallelism. And this kind of one of those things you got to kind of think about when you're, the developer mindset changes when we get into these things. Oh, and by the way, we also have a cost-based optimizer that takes a lot of these things into consideration, right? Because where this data lives comes into really the cost of what it actually does to actually execute these transactions. So whole lot on that. Actually, we wrote a Sigmod paper that's pretty interesting. If anybody wants to read that, I think it's just Sigmod and Cockroach Labs. You'll find, I think, that paper as well. But really interesting stuff there as well. So, okay. I'm not going to get into our cost-based optimizer. I could, and I love it, but I think I only have about 20 minutes. We're doing great. We're doing great here. So I touched on this a little bit. Let's get a little more concrete example about latency and what that means from a transaction point of view. In the beginning, back when I was a developer, I had a laptop and I had a database on it, and I coded. It was, I don't know, gosh, I think the first database I used was I think it was Fox Pro. I think it was the first thing I ever built, right? And actually I was building it, and it was kind of in one thing, right? And if you wanted to scale this, you basically got a bigger laptop or you got a big server. And basically the size of the box really dictated how big you got. If you wanted any sort of high availability or disaster recovery, well, you built on one single server and you had this active passive system where you're doing some synchronization between a primary and a secondary. And if the primary goes down, your application is smart enough to fail over to the secondary. And that's it, man. That's been kind of the state of the art. Well, all that changes when we get to distributed systems. These core concepts and the stuff that we've been doing for 30 years or 20 years just doesn't apply in this new world. How do we take advantage of, large cloud resources, massive amounts of resources, and get scale and get resilience and build that into the application? This is exactly what we're doing here, right? So this old kind of monolithic system just doesn't work, right? And here's why, right? Here you have 2 users, one on the East Coast, one on the West Coast. I have this huge instance of this red database in South Carolina. It takes 12 milliseconds round trip from the East Coast, 70 on the West Coast. Poor West Coast users, you have an unfortunate bad experience when you do these complex transactions. And remember, I had this asynchronous replication of this huge, massive database over into another database center. Now, lots of costs here. Remember, asynchronous replication, you're getting egress. It's the same size. The license is the same, all the storage. I mean, he has these huge, huge instances. And so really this works. And this allows us to basically get kind of HA and disaster recovery. But what about this speed of light thing? I still have this problem, right? And so, in the modern world, what you do is you break it down into smaller chunks. You break it down into kind of distributed systems. So in this case, what we would do is say, let's just break this down. And let's say we have, we have 3, 6, 9, 12, 15 nodes of Cockroach running in lots of different places. And now we're going to get really fast access across the entire country. If you're just here in the United States, we can do this across the planet. But also we can survive these failovers as well, right? We can expand this footprint. Now we're shrinking the time it takes. Now, time in a transaction is a really tricky thing. We're going to talk about how we speed up time here too, but there's this thing called the 100 millisecond rule. And 100 millisecond rule is basically under 100 milliseconds, humans can't really discern it as real time or not. They're like, yeah, that's real time. Over 100 milliseconds, we can actually kind of identify a delay. And so this gets really important in certain applications, but honestly, I think users, this is what they expect in these days, right? So now when users are, say, accessing from Phoenix, they have this kind of really, really quick, 7 millisecond round trip from the app to the data center. So we're talking about, 24 milliseconds for writes. So we're getting this kind of, say this guy's data was up here in US West, right? This person, right? So it's 7 milliseconds to here and another 24 milliseconds up to US West, right? So the total time is 32 milliseconds. On the East Coast time, oh gosh, I'm getting this 20 millisecond, write time. Awesome. And this latency equality across the entirety of the country. And we can do this at planetary scale. So what happens when, something goes down? Oh man, what's going on with my slides here? What happens when, say, US West goes down and there's an outage? Actually, this person now has the same exact latency as they did before because they aren't even going to US West. They're going straight to US West 1, right? And now we have this 31 millisecond write time return trip, right? It's actually the same. And we have now survived the failure as well and have these huge, massive, complex undertakings of active, passive, and extra software and logic and all these different things. I don't have to shard the database. All this is actually just done automatically by spinning up nodes in new regions. The database takes care of all of this. So this can't be easy to do. It actually is. We actually have made it. We've simplified this down to, oh gosh, y'all, I'm sorry, my slides are really slow today. Down to a couple of different, statements that you can have in the database itself. Just a quick little DDL. We define cluster regions. You define database regions, and it's really as simple as a couple things. This is all outlined in our documentation. I'm not going to go through the example, but we've done a couple of different things here. In fact, I can change the survivability goals of my entire database with one simple command. By default, we're going to basically come down to survive, the failure of an availability zone for every row in the table. But say you wanted to actually survive the failure of a region. So survive an availability zone just means like, okay, if I have 3 nodes and they're in 3 different AZs in a single data center, great. I have 1 copy in each AZ. Great, I'm good. What actions if you actually want to survive an entire regional failure? Simple alter database, survive region failure, and it's going to now start redistributing the data where it needs to be so that I have 1 copy of that data in 3 different regions, right? And so there's really kind of cool stuff there. We can get really, really granular and where data lives, and it's really down to each table and what you want the policy to be. Some tables you want to be everywhere all the time, so I have fast access to it. We could do like follower reads. There's lots of different things. We can do, select as of time. Lots of different configurations here in terms of latency. And survival, we're just making it as simple as some simple statements that you actually put in the database. All right, so last topic here. We are 45 minutes in, cruising through. And this is really some magical work that was done by the team here in terms of how do we actually optimize these transactions when they are, globally dispersed. Like I said before, the speed of light is no joke. And when I have, these things happening, if I'm doing a quorum and I have a Raft leader in New York and I have, stuff happening in Sydney and another thing happening in, say, Moscow or something, right? Like I have this data spread across the planet, but we're talking about huge, massive, latencies that have to be contended with. And so there's a lot of things that we've done in the database to contend with this. And so let's look, side by side, what this would happen in kind of serial versus some of the things that we've done here, right? And so in serial, we're going to write a transaction and we're going to write this transaction record first to say, hey, pending, right? That's going to come back and it's going to say, okay, great, I'm pending. And then I'm going to write the car record. Okay, great, that's cool. It's going to come back. And then I'm going to write the Niger record. Okay, that's good. And then I'm going to say, hey, commit, because these 2 things are cool. And I've got to wait for that to come back. So the round trip time to actually make this happen is the compilation of really 4 different round trips back and forth. Okay. Now, the first thing we did was actually, lazy commits and pipelining of transactions. So what we're going to do is start off by saying, hey, let's write this Carl, let's write Nigel at the same time. They both come back, and then we're just going to do the commit, right? So we're being lazy in the beginning about the pending. We're just going to do this commit at the end. We're going to come back. Now, we shrank the time by, about a third here. And so this is kind of what we had done, for a while. And this really kind of helped us kind of get huge, massive performance increases in these things, right? We reduced the latency to just 2 round trips, right? We have this kind of staging transaction state that I talked about a little bit earlier. Remember when the records went to yellow? That's what we're doing there, right? And so all this happens in flight, and it really allows us to kind of reduce this latency down in a lot of the cases. Now, there's a bit of software engineering here called parallel commits. I love talking about parallel commits because I think the first time we talked about this, people were it just blew their minds. I think if you ever heard of Jepson, some of the Jepson tests that Kyle runs on databases, I think the first time he saw this, it's like some weird black box. I don't know how they did this. It's amazing. This is some really cool software engineering again. And so what we're doing here is we said, look, we have this thing. We want to write Carl and Nigel to this database. So we're going to start off the same way we did before. We're just going to go ahead and start, writing these records, but we're actually going to send along this staging record at the same time. Basically what we're doing is saying like, look, if on one node, I can basically say, look, Carl and Nigel are committed and all of the information around this looks like the same way. And I can send all this over. And on the other side, I say, hey, look, this all looks about right. Everything around it. And here's the 2 records I can commit. I can actually come back and just say, this is going to commit right away. And so basically what we've done, we've committed all of these things at once. And we've this kind of centralized marker that we've been using before really becomes distributed across the various different versions. And so the parallel commits is allowing us to do things at the, getting closer and closer to the speed of light. Like, look, we can't change the speed of light, but we can kind of change the package that's going over. And that's really what we're doing here, y'all. Some really kind of more advanced topics. But again, I think these are the things that you think about when you're doing distributed systems, because, well, the speed of light, you're just, I would like to be here when we beat the speed of light, but I don't think it's going to happen in my lifetime. So, okay. This has all been proven. We get questions. Did you prove this with TLA Plus? Yes, we did actually. So we've been through all of the topics. That's the core of the main pieces of the architecture of Cockroach. Now, this is Cockroach Database. Now, Cockroach Database is available in 3 different ways, right? There's this self-hosted where you're managing it yourself and implementing it, doing a lot of these, adding new nodes and these different things. We also have a managed version of this, CockroachDB, Cockroach Cloud right now. It's really Cockroach, like a dedicated managed instance of this where you don't have to spin up nodes and servers, and we give you the SRE and all this. And then we actually have a serverless version of this, which will be really interesting as the fall comes on, as really, delivering consumption-based pricing, these various different things. And so I think it's kind of a really interesting 3 different ways to actually consume. But before I go into the final couple slides, somebody was actually asking about, Kubernetes and how do we actually deploy on Kubernetes? Well, I think Keith had some additional answers, but, we are very, very similar to that. And when I think about clusters and cluster management, especially in Kubernetes, do I want to manage one single cluster across multiple different regions? Well, that's really tough. Single control plane's tough. Well, why not just implement the database as a single logical database and federate at the data layer, right? So we see customers doing this all the time, right? And so this is kind of that concept. We also have a Kubernetes operator. I know this slide needs to be updated. Forgive me, Keith. I know there's been a new release. My bad, y'all. But we do have an operator for Kubernetes that makes it really simple for all the day 2 operations. The simple install and getting it to run with Kubernetes on stateful sets is pretty simple and straightforward, but yeah, we're actually really, really good for these sort of things. And people all over the place are using us for lots of different reasons. We're happy to talk to you about any one of the use cases or workloads that we're out there working with. If you want to go learn more about Cockroach, go check out Cockroach University. Lots of hands-on coursework. We're adding new courses all the time. The team does a phenomenal job. But if you want to get started right now, go check out Cockroach Cloud. We have a free version of this. CockroachDB serverless will be here just in no time. We actually have a free tier right now if you want to start playing with that. But really, this presents kind of the easiest way to consume Cockroach right now if you wanted to go out and try that. So with that, I think that's all I had. I don't know, Keith, are you still on? Did we answer all the questions? Was there anything that we should talk through?
I did answer all of the questions. That doesn't mean that we couldn't talk through a couple of them. I think the most interesting one was around storage in a distributed system and what we think kind of the right way to deploy CockroachDB on different storage patterns is. If we wanted to chat about that, we could talk about that.
I would love to, Keith. I mean, typically with storage, there's the storage pattern. We also get into kind of a lot of these conversations, like what's the recommended storage per node, right? What are our limits there? So how do you talk about it? How do you talk about storage levels and then distributed storage underneath, Keith?
Yeah, so there's performance stuff that we need to talk through, and then there is survivability things that need to be considered. So at a minimum, CockroachDB requires 500 of something called IOPS, which is like asynchronous read-write operations per vCPU per server, right? Now that's the minimum. Most of our customers are running a lot more IOPS per vCPU than that. If we have less than that, the database can't kind of do its basic operations. We've scaled that up to, 10,000 IOPS per vCPU. And in certain circumstances, you still get it kind of a linear performance increase by increasing the performance of your storage, right? So because we're already managing replication and because we're a distributed system, that opens up the opportunity to use what's something called direct attached storage or local storage on your servers. So if you have an NVMe or SSD device that has really good blazing fast IOPS, because the database is doing 3x replication for you as a minimum by default, you can pretty safely run that kind of a configuration. That's not always available, right? Because you still want that, if you're in Amazon, for example, if your node restarts, those aren't persistent volumes. The direct test storage is persistent volumes. So in that scenario, we would use offboard storage, right? We use EBS volumes. We'd want to make sure we provisioned sufficient IOPS for the number of vCPUs. So, and it's because most of the cloud providers give you like 5 to 10 IOPS per gigabyte of storage. You may have to provision a slightly larger storage volume per node to get the IOPS that you need. The tricky bit to remember there is when you're using offboard storage, it's really important that we don't persist multiple replicas of the data to the same storage device. Now, in Amazon, that's really easy to do. You just make sure that if you're running in a single region, that you span your cluster across all 3 availability zones, right? If you were to do something similar in a like a hybrid deployment, or where you were going to be running in one of your own data centers or across multiple of your own data centers, you'd want to make sure that locality information about the storage array was being surfaced in the database configuration. We do support that. I won't kind of go into the really nitty gritty details on how to tag nodes with locality information, but effectively we need to treat all the nodes that are attached to a single storage array as a single fault domain from a replication perspective, so that we don't create a potential single point of failure in the database. Hope that makes sense.
Go on, buddy. Sorry.
I was just saying, I hope that made sense to you.
Yeah,
it makes sense to you. It's not going to make sense to anybody else. So
it does. And there's just a lot of complexity when it comes into those sort of things. Honestly, to me, use CockroachDB managed or Cockroach Cloud, and we actually just take care of all those things for you, right? And so I think, there's ways to, if you want to actually go out and configure all these things, or you just allow it to us to do it, right? And so one of the other questions was, how does the connection string look? Do we configure all the nodes in the string? And I think, Keith, this comes back to kind of how this gets deployed. I mean, basically we're setting up a load balancer and everything in front of this and then you're hitting things, right? I mean, is that how you answer that?
Basically, yeah.
Yeah. Yeah.
You know, the specific implementation details on what we recommend for any given customer's environments can vary slightly depending on what exactly you're trying to accomplish. I think the important thing for folks to take away is that we can support a lot of different topology patterns based on the primitives that we use to build CockroachDB from the ground up. Yeah. So we enable a several system of record deployment patterns in cloud native ecosystems that weren't possible before CockroachDB was in existence.
Yeah. Yeah, and if anybody does want to learn more about like connection string, how that all works, plenty of stuff in our documentation explains exactly how that works, and go out and try it. It's pretty simple to actually get up and running pretty quick. So last question here, Keith. And, how does maintenance of the database, we got to auto reclaim space, say nodes go away, say the database shrinks, that sort of thing. I mean, just the reorganization of that data is using a lot of the same protocols I said. And then actually the third part of this was run stats, but how is that working, Keith?
So unlike a traditional NoSQL database, we have anti-entropy protections built in.
Right.
So a lot of stuff that you would have to do in something like a Cassandra, where you're running a secondary service that goes and kind of does compactions and stuff for you, all of that happens automatically in CockroachDB. We wouldn't be able to guarantee our ACID compliance if we didn't do that.
That's right.
The biggest spot where this becomes like a customer facing impactful is time travel queries. So by default with time travel queries, we keep the old versions of a record around for 25 hours. So you can do time travel queries up to a day before any particular point in time. So past that window, that's when we do the kind of long-term KV store cleanup. So data that's more than roughly 24 hours old will automatically get compacted and managed that way. Stuff that's nearer term than that may you may see multiple versions of that record available for a time travel query, which is probably what you want in that scenario.
Yeah.
As far as kind of the maintenance goes, like we auto generate stats, we auto reclaim space after 25 hours. We allow you to do online schema changes for changing the data structure. That includes primary key changes. So there's no kind of manual DBA maintenance there that needs to be done for any of that work.
And all of it done in production, right? And I think that's the key thing here, Keith. I mean, without downtime is one of those core things. And honestly, a core principle of distributed systems. How do you do these things without taking things offline? And using the concept of being distributed to actually deliver that as a value, right? So, and you talk about point in time queries, it's point in time back up and restore as well, y'all, which is kind of cool. So, thank you, Keith, for helping out here. We are at the top of the hour, so I do want to be respectful of time. And thanks for helping out with all the QA, buddy. I haven't talked to you in weeks, but good to see you.
Yeah, anytime. I turned my camera on, but I wasn't expecting to talk today.
Yeah, that's good, buddy. So, and thank you everybody for joining today. I hope this was valuable. Again, we do have a survey at the end of this. If you could please fill out that survey, it'd be wonderful. And have a great day.